Before we move on to calculating the pH for a weak acid, strong base titration, or the other way around, a weak base with a strong acid, let's examine a little bit more the shape of a titration curve. So up here I'm going to draw the shape of a strong acid, strong base titration curve with the base being the titrant. And down here I'm going to draw the titration curve of a weak acid being titrated with a strong base, such as NaOH. So let's draw the shape of a strong acid, strong base titration curve. It starts off at a very low pH and it's fairly flat. It goes up a little bit, and then when we hit the equivalence, or we get very close to the equivalence point, the slope drastically increases, and then after the equivalence point it kind of levels out at a very high pH. And for a strong acid, so I'll say strong acid, strong base titration curve, right here is the equivalence point, the point where we've added the stoichiometric amount of base to completely react with the acid. That's right here. So that's the equivalence point. And in a strong acid, strong base titration, that will be at pH 7. Now, you'll also notice that this part of the curve is very steep. That's important because we want to choose a pH indicator that will change somewhere in this region. And preferably, we want the pH indicator to start changing just barely after the equivalence point to maybe about up to there. Hopefully, it's completed its change in that range. And that's one of the reasons why we like to use phenolphthalein, because that is approximately the range that phenolphthalein changes. It's also a convenient indicator because it goes from clear to pink, and it's easy to see the appearance of a color rather than, say, a change of a color. Some indicators change from yellow to red, and that change is not quite as dramatic as changing from clear to some colored solution. So there are some advantages to using phenolphthalein as an indicator. But the fact that it changes in this range right here is very important for its use. And part of the reason for that is because we'll have smaller amounts of error when we're doing this analysis, because we want one drop to change the color dramatically. And so since the slope of this line is very high right here, a very small change in the x causes a very dramatic change in the y. And this will increase our signal, or the thing that's changing, and in that case it's pH. And remember, a pH indicator is just a weak acid or a weak base that will change color from one form to the next. And so all of those will change at a particular pH, very near its pKa, and we want to set that range somewhere where we're getting a dramatic change in our solution. We would not, for example, want the indicator to change over this pH, because it's a very large, wide range of volumes that it would take to get there, and it's also not very close to where the equivalence point is, which is actually what we want to measure. So that's just a little bit about indicator choice. All right, let's talk about what happens when we have a weak acid being titrated with a strong base. Now, in case you're wondering what would happen if we titrate a weak acid with a weak base, well, we just don't do that because it would complicate our lives unnecessarily when doing calculations or making sure the reaction has actually gone to completion. So instead, we'll always use at least one of the substances to be strong. Now, when we start off and we haven't added any hydroxide, so say NaOH, and let's just pick acetic acid roughly, because I know approximately how to draw that titration curve, although they're all very similar to each other. It will start off fairly low and have kind of a little bit of an upswing, and then there's a very shallow portion to the curve, and then we'll reach the equivalence point and we'll have, again, very similar to this, the strong acid strong base curve, but it's this part right here in the middle which is a little bit different because we've got this little curve up and then it behaves kind of like the other curve. And this portion of the curve right here is the same because, well, in both cases, we have an excess amount of strong base, right? We have an excess amount of strong base going forward here after the equivalence point. And that will be the same down here. We'll have an excess of strong base. So this back end of the curve is going to look very similar in pretty much every titration that we're using a base with. I can draw what a titration curve looks like if we're titrating a base with an acid next, but we'll get there. So at the halfway point right here, half of the equivalence point, the pH at that point will be the pKa, right? Because at that point, there's an equal amount of the weak acid and its conjugate base. Because when we're doing this, we're actually just converting weak acid into weak base as we add the strong base in. I can write out an equation to illustrate that. We have acetic acid plus NaOH, but we'll just write the net ionic equation, so OH minus, and that will go to the acetate ion and water. So in this case, we're just taking the proton off of there, but this does have acid-base properties to it, and so remember from buffer equations and buffer calculations, if we're at the halfway point, we'll have equal amounts of each of these in there, and our Henderson-Hasselbalch equation will indicate that the pH is the pKa value. And so that is one way to determine a pKa, or a Ka for an acid, is to do a titration, measure the pH as we go along with the titration, determine the equivalence point, which will be at the steepest part of the curve, right here. So there's the equivalence point. And another note here is that since when we get to the equivalence point, all of this acid is used up and converted over into this weak base, we'll have a weak base in solution, which means that the pH right here at the equivalence point is above 7. So I'm going to write 7 down here a little bit lower because that pH at the equivalence point is higher than 7 because we now have a base in solution. So this is how the titration curve looks. Now what would happen if we wanted to calculate what the pH is along the curve? Well, we just did a video on how to calculate the pHs along this curve, but this one is a little different because it has different spots along where we have to treat things in a different manner. So right here, if we've added no titrant in, then we just have our weak acid and water in the solution. So we'll need to use an ice table with our Ka to determine, and the concentration of this weak acid to determine the pH at that point. Then, after we start adding some base in, there will be some weak acid and weak base in solution. That is exactly what a buffer is. So we'll have these two things in solution. This will go away because it will react with our acid right here to make some water and some of this. At that point, we will determine how much base and how much acid is in the solution, and then put that into our Henderson-Hasselbalch equation using the pKa value, and then we can determine what the pH is at any given point along this portion of the titration curve. And that portion must include where we have weak base and weak acid. Once we get up to this point right here, which is the equivalence point, we will have used up all of our weak acid, and we will have used up all of this strong base. So at that point of the titration curve, only our weak base is in the solution at that point. Therefore, we'll have weak base and water. It's very similar to the situation over here where we just had weak acid and water in the solution, but now we have weak base. So we'll need to use an ice table with the concentration of weak base, keeping in mind that we have added some volume of solution to it. So the concentration of weak base is not the same as the acid that we started with. We will have to take the number of moles of this divided by the new total volume. Once we have that, we can use an ice table with our Kb value to find the pH here. Again, remembering that when we have an ice table, we'll be calculating directly from that hydroxide ion concentration, and we'll have to convert that before we can do our pH calculation. After the equivalence point, the calculations is exactly the same as in our strong acid, strong base calculation. What will happen is we will use up all of our weak acid and we'll have some strong base left over. Now, you might say we also have some weak base left in solution too. And that's true. We do have some of this in solution, and we'll probably have more moles of this in solution. Certainly, if we just move a little bit beyond the equivalence point, we'll probably have more moles of this than we have of that. But this is very weak compared to our strong base. It's so weak that you can ignore any contribution of this weak base to the pH when we have something that's strong still in solution. So at that point, we'll only need to determine how much of this is left over, and then from there, we'll determine the concentration of OH and then calculate the pH, just like we did in the strong acid, strong base. And to further convince you that that is the case, let's look at Le Chatelier's principle. I'm going to write the Kb equation down here. Let's see here, H2O. Now, you'll notice that one of the products of our Kb reaction is hydroxide ion. Now, what does Le Chatelier's principle say? If I were to add in some hydroxide ion from an outside source, such as a burette, then that would shift the equilibrium back towards the reactants. So in the case of this is already a weak base. If we shift this back, we didn't make much of that in the beginning anyway, but now we've added some in, it shifts the equilibrium back this way, we make even less contribution from our weak base. And so that's yet another reason why we don't have to consider weak things in solution if we have a excess of something that's strong in solution. So that is the part of a titration curve, and we'll need to keep this in mind and keep in mind where we are in this titration curve when we're doing calculations. That can help us determine what we're doing, and keeping in mind that the equivalence point of a weak acid strong base titration is greater than 7 will help us when we're calculating the equivalence point here, and that will help us know, did we do it right? If we have a pH greater than 7, that's a good indication that we did. And again, one of the reasons why we would want to know what the pH is at the equivalence point is that so we can choose an indicator that's just beyond the equivalence point. That will give us the best detection and the best results in terms of error and quick analysis.